Hello, today we're going to go over mass spectrometry. Mass spectrometry is a technique that separates particles according to their mass. It's used to measure the percent abundances of isotopes of an element. Okay, here we have the mass spectrum of chlorine, and the positions of each peak on the x-axis indicates the mass of the isotope. The intensity or height of the peak indicates the relative abundance of the isotope. The intensity of the highest peak is usually set to 100%, and the intensity of all the other peaks is reported relative to the most intense one. So we are going to go over how you would calculate the percent abundance of each isotope. So for chlorine 35, we are going to put the part, just like any percent is calculated by taking a part over the whole and multiplying that by 100. That's how we find any percentage. So the percent that you got correct on a test would be the part over the total number times 100. That would tell you what percentage you got on the test. So for chlorine 35, the part that is 35 is 100% intensity over the part that is chlorine 37 plus the part that is chlorine 35. So I would estimate that this is about, let's say, maybe 45 or 40. Let's say it's 40 over 140. When you add the 100% plus the 40% up times 100, and we would get 100 divided by 140, which is 71.4%. Okay, so that equals 71.4% of chlorine 35. The chlorine 37 would be the part that's chlorine 37, so we're going to say 40, that's what we estimated it to be, over the total of 140 times 100, and that is going to be, it's going to be the difference between 71.4 and 100, but we'll do it anyways. 40 divided by 140 is 28.6%. That's going to be 28.6% chlorine 37. So that's how we find the relative abundance of each isotope. In the next slide, we're going to use this percent abundance, change it to its its decimal form, so 0.714, 0.286, to find the actual average mass. So to find the average mass, you're going to do what we just did. So they found these percentages of the two isotopes of silver up here, Ag109, Ag107. They estimated the highest peak to be 100 and the slightly smaller one to be 92.9. So we've taken the part that is 100 over the total, where we add those two together, times 100, and they found it was 51.84% silver 107. And then they took the part, 92.9%, over the total, 192.9 times 100, and they found it was 48.16% silver 109. I think that these two things are actually flip-flopped. I think that these should be switched, because if you look, silver 107 is the one that's just slightly below, and then it looks to be like the 109 is the one that's at 100. So I believe this should actually be 109, and this should be 107. But nothing in these calculations that we're doing in AP Chem is going to be exact. So these are all approximations, so we can estimate what would the average mass be close to, not what it would be exactly. Okay, so anyways, once we have these percentages right here, oh, my sprinklers are going off, sorry guys. The percentage is changed to a decimal, just like I said. So right here is this percentage multiplied by the actual mass, 106.905 AMU. That's the actual mass of silver, 107. And this is taken into account the actual mass of the protons and the neutrons in the nucleus, not assuming that they're one. This we would not be able to figure out unless we were given this number, or if we were given the mass of protons and neutrons exactly. Then we could find out what the actual mass would be. Okay, based on how many protons and neutrons silver 107 and 109 have. Anyways, they changed this right here, this percent, to its decimal right there, times the mass of 109. We could just call this 109, and we could just call this 107. They are pretty close, and we would get an answer that's fairly close to the final right here. We can also, if it just had multiple choice and they were far enough apart, we can definitely estimate what the average should be. If it's about half 107 and half 109, because they're almost the same exact intensity, then halfway between 107 and 109, the average should come out to about 108. Okay, and it does hit fairly close to that 108. So this is most likely a multiple choice type question. And so we would have answer choices, and if they're close enough, we wouldn't have to do any of the math. We could just estimate it to be 109. Okay, so number 79 in the back of the chapter, the mass spectrum for europium, EU, is down here, and it wants us to determine the atomic mass of europium. So again, this is one that's really hard to estimate, but I would say that the 153 is at 100%, and this one, let's call it, if it was halfway in between, this would be 75. Let's call it about 90%. So I'm going to estimate this to be 90%. Okay, so that means the EU 151 is going to be the part that is 151, so 90, over the total 100 plus 90, which is 190, times 100, and we will find that the mass, the percent abundance, I should say, 90 divided by 190 is 47.4%. So this equals 47.4%, and the europium 153 is going to be 100 over 190 times 100, which should equal the difference between that. So it should be 53.6% europium 153. Let's do that math just to make sure that my brain is working. 100 divided by 190 equals, oh, good thing I checked, it's 52.6. There we go. Now it's correct. Okay, so that is only the first part. We get to do the second part, which is to change these to the decimal form and multiply by the actual mass, 151, and change this to the decimal, times the actual mass of 153, and then add them up. So let's do that over here. So we have 0.474 for the percent of 151 plus 0.526 times the mass of 153. Okay, and so we need to multiply these out. 0.474 times 151. Whoops, clear. 0.474 times 151 equals 71.54. 574. That's the ugliest 7 ever. 574. It's still going to be fairly ugly. You guys can do it nicer than that. Okay, 71.574. And then we have 0.526 times 153, 80.478. Okay, then last but not least, let's add those two together, plus 71.574 equals 152.05. So this is going to be our average mass for europium, 152.05 AMU. All right, number 80. Number 80, we have the mass spectrum of rubidium, Rb, and it's telling us that there are two isotopes. So we can see there's two peaks there. One is at 100, the other one is below 50. So this one is going to be 100. And let's say that this one over here is, I'm going to say 40. It's a very rough estimate. Okay, so the percent that is RB85 is going to be that 100 over the total of 140 times 100. And the percent that is rubidium 87 is going to be 40, the part that has a mass of 87, over 140 times 100. Okay, then we need to do these calculations. So let's do 100 divided by 140. 71.4. percent here. And 40 over 140 times 100. 28.5. 28.6%. Okay, so these are similar to the chlorine that we're looking at earlier. So we're going to change these percentages to decimals and multiply it by each mass and then add them together. So we will get 0.714 times the mass of 85 AMU plus 0.286 times the mass of 87 AMU. And we get 0.714 times 85 is 60.69. Plus 0.286 times 87, 24.882. Add those two together and we should get our average mass. Plus 60.69. Oh, clear. Okay, we have 24.882 plus 60.69. Why does it not put the decimal in there? 6 0.69. There we go. 85.57. So our final answer, 85.57 AMU. That's really ugly. Let's write it over here. 85.57 AMU is our final answer for the average atomic mass. Okay, and so what this 85.57 is telling us, it's closer to the 85 than it is to the 87. So we can know that there's a greater abundance of the isotope 85. If we were just told the two different isotopes and the average of the two, we know which one there is more of based on the average being closer to that number. All right. Okay, so now the mass of lead is down below. Estimate the mass and percent intensity values from the graph to 3 significant figures. Okay, 3 sig figs. So, oops, that's not straight. You guys can do a better job than this. It's hard to draw these lines on this pad. Okay, so I'm going to estimate this to be 5%. I'm going to estimate this to be 47%. This one is about 40%, and this one is 100. Okay, so to estimate the mass, we're going to have a lot of work to do. We have 204. Okay, and actually I'm going to do that on the left side so that I can do the last part on the right-hand side. Okay, so over here I have 204, which has an intensity of 5. Over the total, we're going to have to add up all of the amounts here. So let's add clear 5% plus 47 plus 40 plus 100, 192. Times 100. Okay, then we have 206, which has an abundance of 47 over 192 times 100. 207, which is going to be 40 over 192 times 100. And last but not least, 208, which is going to be 100 over 192. Okay, and let's calculate those amounts. So we have 5 divided by 192, 0.0543 percent. 47 over 192, 24.5. 24.5%. We have 40 over 192. Oops, clear. 40 divided by 192. 20.8%. And last but not least, we have 100 over 192. 100 over 192, which is very similar to last one, 52.1%. Okay, so now we're going to take each percentage and multiply it by the mass and add them all up. So we're going to need some room over here. So we have, I wrote this wrong, didn't I? This is 5%. I'm going to do that one more time just to make sure. Oh no, it's 5 over 200. I was right the first time. 5 over 192. Nope. 5.43%. Okay. I'm glad I fixed that. All right. So we have 0.0543 times 204 plus 0.245 times 206 plus 0.208 times 207 plus, I'm going to write it down here, 0.521 times 208. Okay, equals, so let's do all of these. Lost my calculator. All right, 0.0543 times 204, 204. This thing's being very sticky. Okay, so we have 11.08 plus 0.245 times 206, 0.245 times 206, 50.47. Okay, then we have 0.208 times 207, 43.06 plus last one, 0.521 times 208. Okay, so we are adding 108.37. And then add them all up. So that one plus 43.06 plus 50.47 plus 11.08 equals 212. And that is telling me that I did something wrong, which is great. I do not have you guys here to correct me on each step. 212. Okay, so this is totally wrong. That would be 3 significant figures, though, is all we need to estimate it to. How do I know I'm wrong? Because it has to be somewhere between 204 and 208. So I am going to go back over that one and redo it. Okay, hopefully correctly. But you guys can see all of the steps there, so I may leave this in so you guys can see the process still. Okay, use the mass spectrum of mercury to estimate the atomic mass of mercury. Estimate the masses and percent intensity values from the graph to 3 significant figures. This is the last one of this type. Okay, so let's go ahead and go through this one. It's going to be a doozy, just like the last one. Hopefully we get it right this time. Okay, and you guys are going to maybe be mad at me, but I'm going to ignore this guy right here. He's so tiny compared to the other ones that I'm not even going to worry about him. So let's estimate our percentages here. Okay, I'm going to estimate this to be about halfway would be 25, so I'm going to say 35. This one is about 55. This one is pretty close to 75. This one is, I would say, almost the same height as this one, so 35, 100. That one's easy because the top one is always 100. And this one looks to be about 20, maybe a little below 25. Let me say 22. Okay, so we're going to have to do all of these percentages. So we have 198. Let me go ahead and start way up here. 198 is going to be 35 over the total, and the total is clear 35 plus 55 plus 75 plus 35 plus 100 plus 22. 322. Okay, and let me go back and check these numbers because this calculator, for some reason, it doesn't want to click on the actual numbers. 35 correct, 55, 75, 35, 122. Okay, 322. So the total is 322. Okay, then we have 199, which is going to be 55 over 322. $322 times 100. I'm going to slow down a little bit because I'm rushing. I don't want to make another mistake and have to redo this one as well. Okay, 75 over 322. 201. Why does this one have to have so many isotopes? 322 times 100. 202 is going to be 100 over 322. And 204. What happened to 203? Apparently that one's not stable for some reason. That's interesting. It just doesn't exist. Okay, so we have a lot of calculating to do here. Let's get our calculator out and do some multiplying. And I'll check my numbers this time. So we have 35 divided by 322. And you know what I just realized? I'm multiplying all of these by 100 just to move the decimal place back and change it from a percent to a decimal. So I'm going to just write the decimal. 0.109. Okay, that's going to leave me a little more room also. All right, so equals 0.109. Double check that. Yes, okay. Then we have 55 divided by 322. 0.171. Okay, clear. 75 divided by 322. 0.233. $35 divided by 322. 0.109. 100 divided by 322. 0.311. And the last one, 22 divided by 322. 0.068. Then, let's get tricky here. So this is times 198. See that 9? It's a 9. This is times 199. This one is times 200. This one's times 201. This one is times 202. And the last one is times 204. Okay. So we have this 0.068 times 204 equals 13.9. Okay, 13.9 plus 0.311 times 202, 62.8. .109 times 201, 21.9. .233 times 200, 46.6. .171 times 199, 34.03. And 0.109 times 198, 21.6. Okay, last step, add them all up. So we're going to add up this whole entire thing and see what we get. Okay, clear. 21.6 plus 34.03 plus 46.6 plus 21.9 plus 62.8 plus 13.9. Let me check my numbers. 21.6, 34.03, 46.6, 21.9, 62.8, and 13.9 equals 200.83. Okay, and that is in our range. So, and it looks to be almost in the center. These smaller percentages might mean it lies more heavily towards this left side. And let's check mercury 200.83. Let's go ahead down here. Mercury, whoops. Mercury Hg. Yay, we're pretty close. It has an average of 200.59. So that one looks like we did actually do the steps correctly. Okay, that was a lot of work. And I think what I'm going to have you guys do is go back and find my error in this one right here. Okay. So sometimes it's actually, you learn more trying to figure out what in the world did Miss Vargas do wrong, and I'm going to let you guys do that. Okay. That way you can learn from my mistakes. Okay, so this is more like what you're going to see on the, now that we know how to do it, we know all the steps, this is more like what you're going to see on the AP test. So we have a multiple choice question here. Copper has two naturally occurring isotopes with masses 62.94 AMU and 64.93. So it's basically copper 63 and copper 65, and has an atomic mass of 63.55. Which mass spectrum is most likely to correspond to a naturally occurring sample of copper. So we can tell by the average, which is 63.55, that the copper 63 outweighs the copper 65 because the average is towards that 63. So we're going to look for a higher peak at 63. So which one of these has a higher peak at 63? Well, this one just has one peak, so it cannot possibly be it because there's only one isotope there. This one, they're 50-50, so the average between 63 and 65, this would be exactly 64. Okay, it's not that one. And this one looks like the second peak, which would be the greater mass, is higher. So it's not this one. So this has to be our correct answer. The taller peak is at the first mass, which would be 63. The second peak of 65 is smaller. All right, so I hope that clarified those problems for you guys. And feel free to email. We will discuss the problem 101 and see if you guys figured out where the error was in class. Have a great day.